This workshop is one of our series on Introduction to HPC. Focuses on parallel computing because the best way to use the capabilities of our HPC resources is to use parallel computing. So let's get right into it. As we take a comparison between a MacBook Pro, so it has 8 cores, 16 gigabytes of memory, 512 gigabytes on an SSD, costs $2,000. Now, if we look as a comparison to our cluster from Penguin, this one's called Puma. So if you look at the nodes, there are 4 of them that are slid out in various stages. So each one of those is a compute node, and each one of those has 96 cores, 512 gigabytes of RAM, and a 2 terabyte SSD. So just right away, you can tell that there's a lot more capability, particularly in terms of the core count and the memory. So that's one way that the cluster is more powerful. Each of the compute nodes has a lot more capability than pretty much any workstations that you can buy, or definitely any laptop. But much of the power of the cluster comes from the fact that the compute nodes are connected together on a network that gives capabilities beyond single compute nodes. So there are 300 of them overall. So if you do a little bit of math on that, it's over 28,000 cores are available. 156 terabytes of memory, 2 petabytes of shared storage. So this capability is really dramatic, and it's paid for centrally, so you don't have to pay for any of these capabilities. All right, so let's start at the beginning. Serial computing. Things are done one at a time. So sequential execution. You have a problem, it's broken into instructions, they occur one at a time, and they each run on a processor. Pretty straightforward. So if you look at the same kind of process, but we can do it in parallel. So we've broken it into 4 problems with 8 instructions each, and each run on one of the 4 processors. So you'll note here that the problem is divided equally. Instructions run for about the same amount of time, and you've got that number of processes that match your problem. So this is all very good and looks like a good case for parallel computing. The problem with much of the processing happened some years ago with Moore's law. The single core has just got too hot. So the answer to keep Moore's law functioning was to add more cores. So if you look at the bottom left here, it's just a simple image of an AMD EPYC Rome CPU, which we have. The compute dies are little elements that are soldered or permanently attached onto that green board and comprise a number of cores. There's a separate one that handles I/O, which is communication between the cores. So all of the cores are in little groupings, and the groupings are all together on one module, instead of the old days where you just had one CPU core. If you look at the NVIDIA GPU image, you can see that the same kind of thing applies. There are a lot of little dies that have different functionality. That's all embedded on one processor board. We're going to talk about some of the terminology involved: caching, the GPUs, threads, processes. So then when we look at a cluster, the image on the right is a layout of Puma. So in the first column on the left, it's mostly yellow, represents all of the compute nodes. There are, I think, 64 of them in each of those columns, which is actually a physical rack. In the middle are switches that are in green that connect each of the compute nodes together. In rack 5, which has different shades of red, those are more specialized nodes, GPU nodes and high memory nodes. And then rack 6 and the brownish, so it's like a dark yellow, there are some more compute nodes there, and the green ones are more switches. Those are spine switches, which connect all of the switches in each of the racks to each other. So you can see here that there are lots and lots of compute nodes. It's all laid out very logically, and they're all connected together with connections in the green switches. So parallel computing, it's really to reduce complexity. So the images here show the kind of complexity in the natural world and the natural universe. So it takes parallel computing really to be able to analyze these things efficiently. All right, so parallel computers save time. So in the example of the harvesters, if you've got a lot of harvesters, you can do the field in much less time because they're all working together. Same with raising a barn. If you have a lot of people working together, things get done much more quickly. And you can have parallel computing systems which are assembled from components which are somewhat commodity oriented. They're not extremely expensive individually, but they are worth a lot when they're all put together. Parallel computers provide concurrency. So in this example of de novo assembly, you can see multiple things can be done at the same time, and then the assembly is done at the end. Parallel computers let you take advantage of non-local resources. So in the last few years, with a lot of focus on protein folding, a community effort called Folding at Home was run. And you can see an image on the left of the protein, and you can see the folding that goes on, and you can imagine the complexity of trying to compute those. And then on the right is the infamous COVID-19 spike protein. The Folding at Home project, the U of A participated along with the other two state universities, and we contributed the 46 most credits with 55 billion of them by using resources that were not assigned to other jobs. So we were keeping our systems really busy. All right, so now some terminology. A node is the individual computer. And so many of them together comprise a supercomputer, also known as a cluster. So in the image there, what you see is two squares sort of in the middle. Each of those is a CPU, also called socket, also called a processor. So physically, that's where all of the cores reside. There are 48 cores in each of those two, so 96 cores total. In the back, another sort of square there is an internal hard drive. This is actually an image of Ocelote. And in the front, and the sides are the memory DIMMs. And at the front, not shown here, is an interface card, which provides the connectivity, which connects all of the computer nodes together and connects them to the storage. So the next term is cores. So a core is on the CPU. So I mentioned there are 48 on each of the sockets on Puma. What's confusing is that in logical terms, CPU and core are often analogous, whereas CPU is, in physical terms, tends to represent the actual physical device. So it's confusing, but for most of your work, you don't really care what the sockets look like. You care about the workload. So consider the CPU to be the same as a core. So with Slurm, uses that reference. CPU is the same as a core. A process, so it's an instance of a program. It's got access to memory, state, file descriptors. And a task is dividing up sections of computational work. So Slurm allocates one CPU to each task, but you can change that default. Shared memory is where all of the cores have access to the same physical memory, and that's within a single node. Threading is the highest level of code executed by a processor, so each process has at least a single thread. So the term hyperthreading is a little different. That's a physical term. If it's turned on, you can do two processes at once on a single core. We turn that off because our cores are busy all the time, so you don't get any advantage of doing it, and we save the overhead by not trying to do hyperthreading. So in our case, hyperthreading is not efficient. It may be efficient on a laptop though. Right, another term, NUMA, non-uniform memory access. So the memory space is shared. And why it matters is when you get into many, many cores. So if you look at the image on the lower left, you can see that the processor complex is divided into 4. And on each of the 4 is a set of cores. And each of those quadrants has a set of memory channels that go out to the memory DIMMs. So there's channel 0 and channel 1 in the top left. And there are a number of DIMMs assigned to that channel. So the processors in the top left run the memory DIMMs in the top left. So you can imagine there is an efficiency if you keep all of your memory, all of the data in memory that are running on the same cores that manage those memory DIMMs. So very particular codes can take advantage of NUMA for more efficiency, but we run a general purpose kind of workload, so we have that capability turned off. So that's set to NPS1, meaning that all of the cores can address all of the memory. Cache coherence. So let's talk about cache for a little bit. If you look at the picture on the right, you'll see that there's no reference to L1 cache. L1 caching is the fastest. It resides in the processor, so that's why it's not shown as a separate device. The concept here is the processor is running an instruction. We can predict that the next instruction is the next piece of data. So the caching will fetch that data and load it in cache. So when the process is ready, the processor is ready to do the next piece of work, it will pull in the data from the cache, which is very close by and very fast. So it'll make for very fast computing. L2 cache is a little bigger, so it costs a bit less, and it's a little slower. L3 cache is bigger still, slower still, but it's shared across all of the cores. So caching makes things faster. There's a term, cache coherence, and that's when, say, data's in L2 cache, but the processor that's going to run the next instructions is not attached to that L2 cache. So it's got to pull it across from either memory or from another cache. So you lose some efficiency there. There's a lot more to caching and all that information, but again, this is just kind of an overview. Right, so another term, distributed memory. Distributed memory is when you have memory that's shared across multiple compute nodes, and we'll talk about how that is done. We'll talk about message passing and MPI. High throughput computing is computations that are run on a single node, often just on one core. So there are a lot of workloads that people run where they need thousands or many, many thousands of jobs that are run that only use one core each. There's a model called data parallel model, also referred as PGAS, partition global address space. We don't deal with that so much, but there is a lot of documentation and conferences on that whole model. Massively parallel is when you use hundreds or thousands of cores. And then embarrassingly parallel is when each of the computations is independent. So you can just keep scaling out by adding more and more and more cores. You don't lose any efficiency. And we'll get into how that inefficiency works and how it's calculated. MPI, so message passing interface, that's how multi-node communication takes place. So when you are using more than one node because you need more cores or you need more memory. So some of the implementations include OpenMPI, Intel MPI, which we use. We also have MPitch and MVAPitch, but those are not used so very much, at least by us. Okay, really simple view of MPI and OpenMP, just the differences between them. So MPI is focused on having multiple nodes connected together across a fabric and message passing between the nodes. OpenMP is more about a single compute node. So the compute nodes with 94 cores available to Slurm, there are 2 cores reserved for system work. So out of the 96, you can use 94 of them. So that references using threads rather than processes, and there are different implementations of each. So they're different, but they're both designed for expanding the capability of your work to use available cores and available compute nodes. Okay, some of the theory. John von Neumann first wrote about it in the 1940s. That's pretty crazy, so long ago. And the general structure of computers hasn't really changed since then. So you have an ALU, the arithmetic logic unit that does the actual calculations, a control unit that moves the data in and out, and memory is where it gets it from, and then input and output. So those are sort of the really basic design steps. Another basic design, Flynn's classical taxonomy. So originally you had single instructions because you had single cores and then a single stream of data. And so you take in some data, run a calculation, get the output, then do the next one and over and over. So Now we're more into MIMD, multiple instructions on multiple data streams. And there's an example of how Puma might do it over multiple processors, running and pulling in different instructions and running them sequentially or sequential and parallel at the same time. All right, Amdahl's law. So Amdahl's law states that the potential program speedup is defined by the fraction of code that can be parallelized. And you'll see on the left, if 95% of the code can be parallelized, the amount of speedup you get. And then if it's only 90% or 50%, 25. So there is a how many processors you can add to increase your workload, and beyond a certain point, there is no more point adding more processors. You don't get any more speed up. So the other way of looking at it is the greater proportion of your code that can be parallelized, the more the speed up. And that's an example of that. But first, there are two ways of viewing scalability, scaling code. So strong scaling is when you have the same problem, but you add more processors. As you add more processors to it, the job takes less time to run. And so that slope, the black slope, indicates perfect. And then the other one is weak scaling. So that's where you add more processors, but you're making the job more complex. So as you make the job bigger, the ideal here is a straight line. So it requires the job will run in the same amount of time, but you're getting a lot more work done. And as long as it stays straight, you're getting efficiency. And then once the slope starts to turn up, you're losing efficiency. If we take a really simple math example, just to show that, on the left side, there are a million multiplications done, and they're all done at exactly the same time, so that's super efficient. And then the outputs are added together, and they're added together sequentially, although if you remember your grade school math, you don't really have to do the adds sequentially, but in this example, that's how we show it. So to follow the proportion, the speed up cannot be more than 1 over x. If x is 50%, that's 1 over a half. So 2x is the greatest that you can get for speed up. You can't go any more than twice. And then another way of looking at this is efficiency of load balancing. So on the left, the load balance is good. Everyone takes the same amount of time to do their work. And then the other example, which shows bad, if you look at on the right side, if one person takes 50 times, and then the others take 10, 5, 5, 5, 5, 5, the maximum speed up again is 2x because one person takes half the time. Okay, so problems with trying to parallelize. One of them is load imbalance. So when you have data distributions that are not even or uniform, so that's a sparse data set. So an example of stars or fractals, medical imaging, doing rendering. Some parts of the data have nothing in them, and other parts have a lot of useful information. All right, so we'll get a little more into MPI now. So Julia has a language wrapper for MPI. MATLAB has its own. There's a parallel toolbox that we have with MATLAB, and then MATLAB also has a parallel pool workers, parpool implementation. Python has implementations of MPI, but I would just warn that MPI for Pi causes some problems. And so if you are dealing with that, you can contact our consultants and we can help you on, because Python complexities with MPI can be challenging. R is one of our more common applications, really Python, R, MATLAB, Anaconda, so which is kind of Python again, are the most common ones. So what we typically support are OpenMPI and Intel MPI. So you can do your compiling with either, and you just have to be aware that when you compile, you have the right compiler there. By default, we have GCC and OpenMPI, so you have to unload them if you want to use the Intel compiler. Right, so let's look at GPUs. If you go think back to that von Neumann picture from like 70 years ago. The same concepts still apply here. So the arithmetic logic unit in green is where all the computations are done. The yellowish one is for the control unit. And then we have caching on top of that. We have memory, and then the I/O occurs. So if you look at the difference with the GPU on the right, you can see there are a lot more cores, but they're simpler, and the control function is simpler. And these originally were created to do the rendering of graphics for gaming. And so you would load just a little piece of each image into each of the cores. And so you get really efficient rendering for gaming. And the exact same logic applies for now machine learning, where you are, say, loading an image and doing you're trying to do recognition of objects within an image. NVIDIA, which provides our GPUs, has a very elaborate ecosystem. So based on CUDA, and there are a lot of tools that are used. We have the CUDA toolkit. You can do CUDA programming if you want, but many of the applications you use that's already been applied. So we have the libraries for machine learning, and then we have a lot of frameworks that already have GPU support built into them. And I'll just point out Rapids is a very popular one because it has a lot of these, the CUDA functionality built into machine learning support. We have a lot of the applications that already have GPU support. So just some of the ones there, TensorFlow and PyTorch. Of course, MATLAB has built-in support. Relion is for cryo-electron microscopes. And the Rapids that I mentioned, Julia has support, Caffe. So more and more of the applications we have GPU support. And I'll just reference one model that one of our researchers is doing. They break their code up into two parts and run separate jobs. The first part of the work is serial because it's loading data in, and that all just happens sequentially. So they run that part of the job on CPU nodes because we have many more of those. And then they take the output of that work and then they load up a GPU job using Slurm, and they run that work on the GPU node because they can speed up that section of the code by 20 times faster. And then they take the job. When that's complete, it starts another job, which again runs on CPUs for the part that's again serialized. So there are different ways of making your code really efficient, especially when you're doing it at scale. We don't get into parallel programming here. This is really about an overview of how to do things in a parallel manner. There are a lot of courses that you can do on parallel programming, and I've included a link here. The PDF file, which is attached in the same part of our tutorial program, has all of these links, so you can go there if you want to actually get into some of them. So I've included a few links in different places and in upcoming slides. We have some tools for performance analysis. So one of them is HPC Toolkit. Another one is Valgrind. So Valgrind is installed in the operating system on all of the compute nodes. And where possible, when we created modules, if there was an option to turn on support for Valgrind, we would do that. And so if you're doing your own compiles, you might want to check and see if Valgrind support is built in and whether you need to add it. So this part, we just have an example. If you look at the bottom, we have GitHub, and one of the examples is how to run a multi-node MPI job. So there's a simple hello world C code there, and you can compile it using MPI-CC, and then you can run it, and it'll tell you however many tasks you set it to run. It'll come back and say hello from each of the tasks. So it's a really simple process, but here the batch script directives are useful because it shows you how to break them up. So in this case, we've got 30 tasks, 10 of them running on each of 3 nodes. We also encourage the use of arrays, which is supported by Slurm. So you can do that instead of running for loops. So the array can also have dependency sets, so your array jobs will run one after the other. You can use parallel, and that's available as a module. So that's a very popular module that we have. And again, if you see down the link to the GitHub there, we've got examples of how to use that. Doing parallel computing with R, there's a lot of available resources there. And I would just point out particularly the bottom one from Jonathan Dursey in his GitHub. It's got information on how to run using parallel for each big memory and then some of the R packages. So there is a lot of information out there on doing parallel work with R. And for Python, we have an example here. There's this Python script set up on this page. And then on the next page is the Slurm script that will run the Python script that was displayed on the previous page. And if you don't want to have to try to retype all of that or capture it, you can go again to our GitHub and look at that example. Then the last one here we have is just some more references. There are some pretty neat tutorials out there. There's a textbook if you want to look at it, and then I've also included some references to introductory Linux material. So this is one of our series on parallel computing. Feel free to look at the PDF and follow along with some of the examples from our GitHub.